I wanted to emphasize or ask a question. So why do we do asymptotics anyway? And validate the some kind of ad hoc approximations which exist in well, in meteorology, for example. And furthermore, you can also, if you do it rigorously, you can justify the limit equations you have somehow and obtain some kind of error estimates. Furthermore, it's used for the calculation of approximate solutions. So it's also done here when you use the or some type of anelastic equations, because it might be simpler numerically. And then what is commonly not so, or what is not so common, I think you can even use it in the development and validation of numerical methods. So if you carefully look at the asymptotic analysis of your asymptotic regime, you can, well, identify, you can see what should happen in the regime, and you can design your numerical method according to this. And furthermore, you can, in the end, you can test your numerical method with the asymptotic limit equations. My talk was about asymptotically adaptive numerical methods, and you'll probably ask yourself, what's that supposed to be? And here I have a definition from a former colleague from me, Stefan Vater. And he combines it actually with schemes in conservation form, but the main point is that asymptotically adaptive numerical methods are schemes whose accuracy and efficiency do not break down in the vicinity of or in a singular regime. So you would like to design numerical methods which work for some set of equations with a small parameter, and if that parameter goes to 0, you want to behave your numerical scheme in the same way as the equations behave. And even you want, it's desirable to have that your scheme does still work if your singular parameter even goes to 0. Something which is very similar to this definition is the notion of asymptotic preserving schemes. I think Paul Degon, he introduced that, and he mainly defined it in a way that if you have such a small parameter epsilon and a grid parameter h, that the scheme should behave in a way that you can, these two small parameters can commute, and you get to the same solution in the end. Yeah. The outline of my talk is, first of all, I would like to apply this to the governing equations, especially to the shallow water equations. Then I would like to talk about the numerics we developed for that. And recently I developed a multiscale method, which is an asymptotically adaptive numerical method. When you look at the fully compressible equations, you have different types of waves, for example, sound waves, internal gravity waves, and also Rossby waves, which are very well separated, so you have a scale separation between them. And when you look from a numerical point of view, at least the sound waves are usually considered unimportant, and you only want to keep well, the gravity waves and especially the Rossby waves. And well, when I look now in the look at the shallow water equations, we don't have these internal waves here, we just have external waves, especially what's in the compressible equations, the Lamb wave, or in the shallow water equations, then these are the gravity waves, or the inertial gravity waves. And the goal of this whole study was that we want to develop methods where you can do global simulations at high resolutions. So here the goal is, since you cannot resolve these fast sound waves, at least if you use implicit methods fully in time. So you have to get rid somehow of these fast waves in a consistent way. But on the other hand, the long wave sound waves you would like to keep. And also the geostrophic modes. Furthermore, what we have in the atmosphere are source terms, like what comes out of the latent heat release of cloud formation, and this develops some local divergence and acoustic sound waves. But we are not interested, again, in the acoustic sound waves, but merely in the underlying balance behind it. Okay, if we now look at the shallow water equations, this mainly translates, when you look at the non-dimensional form, in small parameters, which are the Fruit number and the Rossby number. And if they are small, you have this, on the one hand, this balance between source terms and the underlying dynamics, and on the other hand, you have the scale separation between the different waves you have in geophysical flows. Okay, and if you look, the main asymptotic limit regime I would like to consider now is the regime of long wave shallow water waves, and they should travel over rough topography, and this topography is time dependent, which might be a little bit unusual, but this actually models the small scale divergence which might be introduced by cloud formation or something like that. And so I have this time-dependent topography. And when you look at this asymptotic regime, you mainly get two different equation sets for the large scale and for the small scale. On the large scale, you have some kind of wave equation with the source term which is coming from the small scale. And on the small scale, you have just a balance between the bottom topography and the divergence of the small scale flow. And this should be, or the goal is that this should be also simulated or modeled by the numerical scheme. So what are the difficulties when you want to compute low Fruit number shallow water flows? The one thing I already mentioned is the vanishing Fruit number, and this induces that the height variations mainly vanish, but they still affect the velocity at leading order. Then this spatial homogeneity of the pressure, or the height in this case, implies an elliptic divergence constraint for the mass flux. Furthermore, we have singularity in the eigenvalues of the Jacobian flux matrix, because here the gravity waves scale with 1 over Fruit number. And this mainly means that at least explicit methods suffer from a CFL time step restriction, which is similar to the fruit number. So, and by using semi-implicit methods, we would like to circumvent that. So, when I now construct the numerical scheme, I would like to have a scheme which is independent of the fruit number, which is conservative for mass and momentum in the case of shallow water equations. Furthermore, it should be second order accurate, which turns out to be not that easy, but at least if you want to be stable. We would like to use the machinery of Godunov type methods or shock capturing methods. So if the fruit number becomes large and we enter the regime of where you can also have shocks, we are some kind of on the safe side that we can use this part of the method. Then furthermore, we would like to solve at most linear scalar equations, so some kind of elliptic equation and nonlinear equation. And furthermore, which which makes the scheme asymptotically adaptive, is that in case of the fruit number, the equation velocities and the final momentum should satisfy the arising divergence constraint. So on the one side, we have the Godunov type methods for compressible flows. And on the other side, if we go to 0, we have some kind of projection method. And that was the first step I looked at, was the derivation of the projection method for the zero fruit number shallow water equations, which is in conservation form, and it is built in the kind that you have three, or the fluxes are computed in 3 steps. First, you have a prediction step, which computes some kind of advective fluxes applied to an auxiliary system, which is hyperbolic in this case. Then to correct the advective velocities, we apply some kind of Mach projection. And finally, in order to get the pressure gradient and the new momentum at the new time step, which satisfies the divergence constraint, we apply a second projection. So here, the Mach projection is just that we apply the divergence constraint about the primary cells, and then we get an update for the advective velocities by the predictor and correction. And if you apply the divergence to this equation, you see that you get a Poisson type problem for H2 here. In the second projection, we would like to have new time level momentum, which satisfies our divergence constraint. And for this, we apply a divergence which is centered around the nodes, so which is for the duals, or for duals, dual discretization. And in this case, we compute the new time level momentum by an intermediate momentum and the pressure or height gradient. And once again, if you apply the divergence to this equation, you once again get a Poisson equation for H2. This projection method could be shown to be an exact projection method, which is mostly the case because we not only adjust the cell mean values of the momentum, new time level momentum, but also the piecewise bilinear or piecewise linear behavior within a cell. So we also have updates for that by the second correction, and then it is an exact projection.
So I'm just curious as to what sort of space you're in here. Is it the previous figure gave an impression that you were able to reconstruct your velocity field at any place over an element, or are you doing? But now the next figure kind of implies that you're doing a piecewise bilinear reconstruction. I mean, you're going between cell centers and faces and nodes, and I just wonder how you're manipulating the data between those different places.
Well, in the end, it's a finite volume method. So mainly you have cell averages within each cell.
Okay.
But by having a second order method, we first reconstruct it by common reconstruction methods with limiting and so on. And then we have a piecewise linear velocity field, and that is then corrected by the second correction. So in the end of the time step, you have piecewise linear velocities which are discontinuous across the cell boundaries. But, well, you discard the piecewise linear reconstruction at some time within the method, because in the first step, you just use a finite volume method. Yeah. Does that answer everything?
I think it does, yeah.
Okay. Well, but by using this, in the end, we have a velocity field which is compliant with the divergence constraint, which means we have an exact projection method. Furthermore, we could show that this method is insubstable, so which means that we rewrote the method to have a saddle point problem, and then by the theory of mixed finite elements, we could show that essentially the momentum field and the pressure gradient cannot decouple. So often in projection methods, you have the problem that you have, for one momentum field, you can have different pressure fields which are somehow in compliance. And so you have an arbitrary pressure field, and this cannot happen in this case. Okay, now when we come to low fruit number shallow water flows, how do we extend the method? So first of all, we decompose the height into a background height and perturbation, which goes with the square root with the square of the fruit number. So this is similar to the zero fruit number limit, where you have just this H2 here, which I talked about. And then the shallow water equations can be written in this way, which is very much similar to the zero fruit number limit. And the only thing which happens is that we have to include the local time derivatives of this height perturbation into our correction steps. So here, for example, we have our auxiliary system, which are, again, the shallow water equations, and only the pressure gradient is taken from the old time step. With this, we already have second order accurate predictions for our advective velocity field by the auxiliary system, which is denoted by a star here. But in order to stabilize it, we introduce this height perturbation term here. And by this, we get an Helmholtz equation for this height perturbation update, which is given here by this term, and these are known either by the predictor step or, well, H0 is mostly is determined by the boundary conditions and the bottom topography. So it's already known. Okay, this is the first correction, and in the second correction, in order to get the pressure term, we first compute an intermediate momentum update, which is given by all what you know by the prediction step and the first correction. And then the momentum at the new time level is given by this intermediate momentum update plus a correction in order to get second order accuracy. And if we now employ a trapezoidal discretization for the height equation, we once again get a second Helmholtz equation for the update of the height perturbation here. Okay, and this is using a trapezoidal discretization, and by using this you get second order accuracy, but you can see that, for example, if you introduce source terms, you get some kind of instability. So often what is used is that you end up by doing some kind of off-centering here in the trapezoidal discretization, but then you are getting first order accurate only. So that's not what we want to do, and so I introduced a variation which is based on the BDF2 scheme of the semi-implicit method. So the momentum is now computed by BDF2 discretization, and then so before we had the advective fluxes were computed at the half-time level. In order to get second order accuracy, we now have to extrapolate these fluxes, and then in the same way we get another Helmholtz equation which is based on BDF2 also for the height equation. And this works very well for when you have source terms, but on the other hand, the trapezoidal rule turns out to be better when you want to compute long wave shallow water, so long wave flows, and it also conserves some kind of energy. So I would like to talk now about the combination of this, and well, here I shortly revisit what I also already talked about at the PDE's conference. So I look at the linearized shallow water equations, and here at the trapezoidal, I have the trapezoidal discretization and the BDF2 discretization of these equations, and if I look at that, I get the following dispersion relation, which mostly say everything about it. So you have the dispersion relation for the exact equations, which is just a straight line, so you have no dispersion. Then you have, and if you look at the dispersion relation of the discrete equations, you see that the waves gets lower the higher the wave number, and even for in the limit you get, for example, zero group velocity. This slowdown is larger for the BDF2 scheme than for the trapezoidal rule. But on the other hand, if you look at the amplification factor as a function of the wave number, you see that the trapezoidal rule in the linear case it conserves the amplitude of the waves of all waves, but the BDF2 scheme damps them. And this essentially helps us to stabilize the scheme. This behavior is further enhanced if you look at larger CFL numbers, then the slowdown of the waves and the damping of the BDF2 scheme is further enhanced. And so we would like to have the desired behavior we would like to have that on the one hand we would like to minimize dispersion for well-resolved modes, and there we would like to use the trapezoidal rule. But on the other hand, the solution should also rapidly relax to the balanced mode in case of short wave number forcing by a source term. And there we would like to use the BDF2 scheme. So we would like to combine somehow these two schemes in one scheme. And this is done by some kind of multi-level method where we separate the height and velocity into quasi-spectral components, which can be defined by some kind of projection operators. Then let's assume that we have two time discretizations, for example, the trapezoidal rule and the BDF2 scheme. And then by doing a convex combination of both schemes with scale-dependent weights, mu and nu, we get another another equation to solve, which is also some kind of Helmholtz equation with a scale-dependent operator here. And the mu and nu are defined in a way that you we derive it somehow automatically, that you have the trapezoidal rule in our case for when you have grid CFL numbers equal to 1 or smaller, and then for larger grid CFL numbers where you cannot anymore resolve the waves, you nudge, or we nudge the scheme towards the BDF2 scheme. So this is how it looks for, well, here I wrote implicit midpoint rule, sorry, that's the trapezoidal rule, but we have two Helmholtz equations and updates for both schemes, and this is how the blended scheme then looks like. Okay, and then if you look at the dispersion relation again, you see that for the long waves, the dispersion of the multi-level method more or less resembles the behavior of the trapezoidal rule, and when it goes to smaller waves, it more resembles the behavior of the BDF2 scheme. The reason why it's somehow here not so nice is more or less that this multi-level method does not have the sines and cosines as eigenfunctions, and then it's not so easy to derive a dispersion relation actually. And I still try to get a better picture of that, but it's somehow not so easy. Okay, how does it look like now for our full nonlinear equations? And here the only thing which is changed is the second correction. So the predictor and the first correction are identical for both schemes. And then in the second correction we have two intermediate momentum updates, one for the trapezoidal rule and one for the BDF2 scheme. And we also have, by this, we have two different Helmholtz problems. And these can be combined in the same way as it was done for the linearized equations. And you get, once again, a multiscale Helmholtz problem where the multiscale is hidden in the scale-dependent operator and also on the right-hand side. And by this, you get an update for the momentum at the new time step. Okay, let's look at some test cases. First of all, I have a very simple test case, which is a weakly nonlinear gravity wave, which is just going into the right direction. And I computed first for fruit number which is equal to 0.1, which results in a CFL number of 0.77 for the advective components of the flow and about 9 for the gravity wave speed. And, well, this is the height field, and if you look at that after 40 time steps, you can see that, so here we are already in the somehow in the compressible regime. So already the black line denotes the exact solution, and already we have a shock there. And then you can see that the trapezoidal time discretization forms some kind of oscillations near this shock. And well, the BDF2 discretization, which is the green line, and I think I have a variation in there, which is the red line. You see some kind of beta behavior, but a little bit of dispersion in there. So the location of the shock is not, or might be not so well captured. And here I also have an off-centered version of the scheme in there, which is the orange line, which, well, doesn't develop these oscillations, but in the end it's first order. So if you look at a further time step, after 100 time steps, the trapezoidal rule gets unstable for the given time step. So I haven't got it in here anymore, but you can see that at least the BDF2 discretizations are still stable, at least. They do not behave so well, but, well, it's an implicit discretization, so I think you cannot hope that it's much better. Then I have the same thing for a much smaller fruit number. And here we are mostly in the asymptotic regime we would like to consider. So we have mostly linear attraction of this gravity waves. And if you just look after 8 time steps, you can see that the trapezoidal discretization, which is the red line, and the blue line, by the way, is also the multiscale scheme, behaves much better than the BDF2 discretizations in amplitude and also in the dispersion error. I said that I would like to have a second order scheme. So I did some kind of different convergence analysis. Here it is also for the weakly compressible gravity wave, and you can see that all schemes have second order accuracy here in the L infinity norm, but you can do the same for the L2 norm. And well, then I have looked at the lake at rest. So you would like to have some kind of so-called well-balanced scheme, so that if you start with a lake at rest and you have well, some kind of non-trivial topography, you would like that the lake still stays at rest and doesn't develop any artificial velocities, which sometimes happens. And so I did this test and computed it for some time, and you can see that the trapezoidal discretization here and the BDF2 discretization, they keep at this rest for the height and the momentum in the infinity norm, and well, the error you get mostly depends on the accuracy of the elliptic solver you're using in your scheme. Then I further looked at the balancing of source terms. So I have here the time-dependent bottom topography, and here you can see what is the result in the height. And furthermore, the red line denotes the asymptotic solution I would like to compare it with. And if you look at this, you can see that the trapezoidal rule does not relax to the asymptotic solution. It merely oscillates around it at each grid point. But if you look at the BDF2 scheme, you can see that after some time it mostly relaxes to the asymptotic limit solution. So that's the behavior we would like to have. And this can be also seen by the multi-level method. That the scheme mostly relaxes to the asymptotic limit solution. Okay, I think, yeah, that's the end. So I introduced the notion of asymptotically adaptive numerical methods and put it in the context of the simulation of large-scale flow at high resolution. And for the derivation of the numerical method, I first introduced a projection method for zero fruit number flows and extended this to low fruit number flows by getting a semi-implicit method. And furthermore, I introduced a multiscale method which incorporates a quasi-spectral decomposition of the data and some kind of multi-grid techniques, which I didn't talk so much about here. And I showed you some test cases. And the outlook is that I still work on the efficient solution of the multiscale method. And also what I didn't tell is that here the results are only for the multiscale method are only for one space dimension. So I have to extend that to 2 space dimensions, but which should be very straightforward. And well, that was from the PDEs a point that this method should be also further applied to more realistic test cases. Okay, thank you for your attention.
Other questions?
Yeah?
This method, like, how do you capture the shocks? We applied to capture the shocks.
Yeah.
So the how do you detect the shock, and do we have to know the position of the shock a priori?
No. So what in the end, when you would like to have an all fruit number scheme, which also works in the compressible regime, you would switch at some point. You would switch the scheme to a good enough type method, which you use in the predictor step, and then well, this scheme would determine or would not need to know the position of the shock or something like that. So when I showed this test case with a shock here, I just wanted to, wanted to see how the scheme behaves somehow in the compressible regime already. But usually one would like to, at this fruit number, you might want to switch more to a good enough type scheme in the end.
So that method will handle it better. That method handles it better.
That might be better in this case, yeah.
When you showed the elliptic systems that you have to solve, I was not completely sure whether the multiscale method needs
This
2
here?
or just 1. No, I think it was even before that. Here.
This here?
That one,
Yeah.
So the multiscale method also uses 1 elliptic problem, or does it have to solve 2?
Yeah. So you have 1 elliptic problem. So for the classical discretizations, you have each 1 elliptic problem.
Yeah.
And then in the multi-level method here, you combine the elliptic operator or the 2 elliptic operators into 1, and you get a new operator which acts on the fine grid. But it's a little bit more complicated because you have to incorporate the multiscale information. And furthermore, when you compute the right-hand side of the problem, you also have to incorporate the multiscale information.
Right.
So
Do you
you
have any information about the structure of that new elliptic system? Is that in terms of eigenvalues and condition number and things like that?
Not so much. So the only thing I have investigated. The only thing I have investigated is that the bandwidth of your resulting matrix gets much larger because you also incorporate somehow a coarse grid, which incorporates very many fine grid cells. But on the other hand, these additional values are very small compared to the, I don't know, grid, for example, the BDF2 scheme. So the difference is not so big in the operators. And so, well, but these are still questions which might have to be further investigated.
Further questions? That seems not to be the case, so let's thank Stefan again.